In the previous videos, we have seen how to use 3 different methods to program multi-GPU platforms. However, letting GPUs to work in their silos and never let them communicate is not likely to be useful. Eventually, the result calculated by the GPUs will need to be aggregated together, and the GPUs need to communicate with each other. So starting from this video, we're going to introduce 3 different methods to allow GPUs to communicate with another GPU. The first method is device-to-device memory copy. So let's see one use case why we want GPUs to communicate with each other. Let's assume our GPUs are running a deep neural network training application, and we're using data parallelism method. When using data parallelism method, the CPU will distribute 4 different training batches to 4 different GPUs. And the GPUs will perform forward propagation and backward propagation independently without communicating with another GPU. So you can either use thread-based method or stream-based method or even MPI-based method to allow them to complete this forward and backward propagation process. After the back propagation process, the gradient of every parameter is calculated, and we need to aggregate them together, update the model, and distribute the new model to all the GPUs so that we can start a new round of forward propagation and backward propagation. During this forward and backward propagation phase, there's no need for GPU-to-GPU communication. But during this aggregation and the gradient descent process, we do need the GPU to communicate with each other. So let's see what method we have. So in general, the aggregation process is to calculate the average of 4 different arrays that is calculated on each individual GPUs. Let's see how we can calculate the average of buffers that stores at the different GPUs. In general, we have this GPU level reduction method. Remember when we talk about the reduction method for GPU program tuning, we maximize the number of devices that can be used, and we perform this application. Then we perform this calculation with the highest level of parallelism. And here, GPU level reduction is similar to thread level reduction. Here, we use GPU 0 to calculate the average between the data that is stored in GPU 0 and GPU 1. Then we use GPU 2 to calculate data that is stored in GPU 2 and GPU 3. And in the second iteration, we use GPU 0 to calculate the average result that is stored in GPU 0 and in GPU 2. And finally, we average the data that is stored in GPU 0 and GPU 4. We get a single copy of the final averaging result. In this way, we get the highest level of parallelism and throughput. So let's see how we can implement this algorithm. We start with this main function. We do not introduce the kernel implementation part because we think the audience should be very familiar with how to write this type of kernels. So let's assume we have a length of data and we're using 8 GPUs. The length here is very short, but this is just an example. It's a parameterized length, so the audience can change it to any value they want. Here we have this std vector and std vector float, which stores the h output. It is actually the input of this algorithm. It's the output of the backward propagation that is calculated on each GPU. It's a vector to vector. It's a 2-dimensional array. The first dimension is the GPU ID, and the second dimension is the index of the numbers. Then we have another variable that is std vector float star. Here the float star is the GPU pointer. And here we have a vector of GPU pointers. Those are the buffers that are stored on different GPUs. Then we have a final result, which should store the final average of the whole array. And it's a 1-dimensional array this time. In stage 1, we calculate the result for all GPU buffers. This is related to the problem we're trying to solve, so we're not going to include the code here. Then we see this special nested loop. We have 2 layers of loops, and we have 2 variables I and j. I is controlling the number of iterations. We start with 1, then every time we shift the digit to the left by 1 digit. That means we're multiplying by 2. In the first iteration, we have I equals to 1. In the second iteration, we have I equals to 2. And in the third iteration, we have I equals to 8. Then we will stop from that point. And in this example, we have 3 levels of iteration, which maps to this layer of loop. Then in the inner loop, we have j equals to 0. And then in the inner loop, we control what each GPU needs to do. We launch 1 kernel in each iteration. We'll start from j equals to 0, then j smaller than number of GPUs, then j multiplied by I multiplied by 2. So in the first iteration, we calculate GPU 0, GPU 2, GPU 4, GPU 6. In the second iteration, we get GPU 0 and GPU 4. And in the last iteration, we only get GPU 0. So let's focus on the inner loop and only look at this small step. We have two GPUs. One is called left GPU, one is called right GPU. In this case, GPU 0 is left GPU, GPU 1 is the right GPU. And then we set the device to be the left GPU. We perform this aggregation process only on the left GPU. We define a left buffer, which is not a newly allocated buffer, but it's just a pointer pointing to the buffer of the left GPU's output. We have another right buffer. So here we need to allocate this right buffer. Right buffer is still allocated on the GPU, but it's designed to store the data that is located on the right GPU. We allocate this buffer with heap malloc. Because we set the device to the left GPU, this buffer will be allocated on the left GPU. Then we use a memory copy D2D, device-to-device memory copy, to copy from the output buffer that is located on the right GPU to the right buffer with a certain length. This API call performs a GPU-to-GPU memory communication. We're simply copying the buffer from one GPU to another GPU. For the rest of the code, is regular GPU programming. We calculate the number of blocks, then we launch the kernel. At this moment, left buffer is on GPU 0, right buffer is also on GPU 0. Then the average kernel should be very easy to write because it's simply a vector add, then divide by 2. So let's look at this loop again. It's a nested loop. The outer loop is responsible for the big iterations, and the inner loop is responsible for launching each individual kernels. And within each iteration, we define left buffer and the right buffer. We copy the data from the right GPU to the right buffer. Then finally, we perform a local kernel launch to let the kernel use localize the data to calculate the average. After all the kernels are completed, we should have the final result ready to be used. The final result is stored on GPU 0. As you can see, this method is very easy to implement, and the performance is easy to predict. So the only overhead is this heap memory copy D2D process. The performance of this D2D process will pretty much determined by the length of the array and the bandwidth between the two GPUs. However, the drawback of this method is that we still need to perform this D2D memory copy, and the kernel cannot launch until all the data is available on GPU 0. So in the next video, we're going to see another method and see if we can improve this process.